In this video, we'll do an example of trigonometric substitution where we'll have an integral containing a squared plus x squared. For this one, we have the integral to evaluate as dx over the square root of x squared plus 4. So in this case, our a is 2 if we do it by trigonometric substitution. So that tells us we're going to let x equals to 2 tangent of theta, which then gives us that dx equals to 2 secant squared of theta d theta. So let's do our substitution. So we have this integral of dx over the square root of x squared plus 4 equals to the integral of, let's see, instead of dx, that would be 2 secant squared of theta d theta all over, instead of the square root of x squared plus 4, this would be the square root of 2 tangent of theta, that's squared, so that would be 4 tangent squared of theta plus 4, which would be equal to the integral of 2 secant squared of theta d theta all over. Now we could pull out a factor of 4 outside the square root, but remember when you do that, you got to take the square root of that 4, so that would equal to 2. And then we'd have times the square root of tangent squared plus 1, or tangent squared of theta plus 1, which is equal to the integral of 2 secant squared of theta d theta all over 2 times the square root of, instead of tangent squared of theta plus 1, we could rewrite that as secant squared of theta. And so that we could then rewrite this integral as the integral of 2 secant squared of theta d theta all over 2 secant of theta, which, let's see, the 2's cancel, secant of theta is cancelled, so this would be the integral of just secant of theta d theta. Now to find the integral of secant of theta, what we're going to do is this little trick where we're going to multiply the top and bottom by secant of theta plus tangent of theta. So we'll have the integral of secant of theta, and then like so we're going to multiply that by secant of theta plus tangent of theta over secant of theta plus tangent of theta, and we have d theta. You might be thinking, why are we doing this? Doesn't this make it unnecessarily complicated? Well, you'll see the reason why, so just trust us. So multiplying this out, on the top, multiplying the top by that secant of theta, we'd have secant squared of theta plus secant of theta tangent of theta all over secant of theta plus tangent of theta d theta. And what we're going to do is we're going to do a substitution where we're going to let u equal to what was in the denominator, the secant of theta plus tangent of theta. Then du would equal to the quantity, well, let's see, the integral of the secant of theta, that's secant of theta tangent of theta, plus the integral of tangent of theta, that's that secant squared of theta d theta. And now if you notice, we have that du, that's the top, d times that d theta, right? So doing our substitution, this then gives us, just becomes, well, all of that stuff on the top is just the du. All the stuff on the bottom is just u, so we have just the integral of du over u, which is equal to the natural log of the absolute value of u plus c. Now remember, we then do our back substitution, plugging in the secant of theta plus tangent of theta back in for u. So this gives us, this is equal to the natural log of the absolute value of secant of theta plus tangent of theta, all that plus c. But remember, our original question was still in terms of x, not in terms of theta, so we need to do another back substitution. Well, we do know that from our original substitution, x was equal to 2 tangent of theta. So that gives us that tangent of theta is x over 2. And then drawing our right triangle where we have the angle theta. So if tangent of theta is x over 2, remember that's opposite over adjacent. So the side opposite of theta would be x. The side adjacent to theta would be 2. And using the Pythagorean theorem, that the length of the hypotenuse would be x squared plus 4. So we could figure out from that, because we know the tangent of theta, like we said, was x over 2, but we also need to know what secant of theta is. Well, secant of theta, that would equal to what? That would equal to let's see, cosine of theta is the adjacent over hypotenuse, so secant of theta would be the reciprocal of that, so that would be what? The square root of x squared plus 4 over 2. So plugging that all in, that we have that our original integral, this dx over x squared plus 4, is equal to the natural log of the absolute value of secant of theta, which was that square root of x squared plus 4 all over 2, plus tangent of theta, which was the x over 2, that plus c. So that's doing it with trigonometric substitution. Now I'm going to show you that we could have actually done this another way as well. And what we're going to use is the inverse of the hyperbolic functions to do this. And for this one, we're going to use the inverse of the hyperbolic sine function, because if you remember that the integral of dx over the square root of x squared plus a squared was equal to the inverse of the hyperbolic sine function of x over a plus c. So what that tells us in this case is that this original integral, the integral of dx over, well, that should be the square root. The square root of x squared plus 4, our a is 2 in this case, so this is equal to the inverse of the hyperbolic sine function of x over 2 plus c. And then you might think, thinking, oh wait, that looks totally different. But remember, there's the logarithmic definition of the hyperbolic, the inverse of the hyperbolic sine function, which was that the inverse of the hyperbolic sine function of x is equal to the natural log of x plus the square root of x squared plus 1. So this tells us that the inverse of the hyperbolic sine function of x over 2 is equal to the natural log of x over 2 plus the square root of x squared. Instead of x squared, that would be x squared over 2 squared, so x squared over 4 plus 1, that plus c. And we could simplify this, so this would be the natural log of, again, that x over 2 plus, now just adding the two terms underneath a radical by getting a common denominator, this would equal to plus the square root of x squared plus 4 all over 4 plus c, and then taking the square root of the top and bottom for that second term inside the natural log, so this would equal to the natural log of x over 2 plus the square root of x squared plus 4 all over 2 plus c. And now since this x over 2 plus the square root of x squared plus 4 over 2, that's going to be a positive value. We could take the absolute value signs away, so you see that those two are equal to each other.